Okay, so let's take a look at your midterm. So we downloaded the study guide from Canvas. And what I want to do real quick is run through two things. The first is the format of your test, what to expect. And the second is the actual content of your test, what to expect in terms of that. Let me preface it with this. If it's on the study guide, it's on your test. If it's not on the study guide, it's not on your test. So hopefully that saves off any questions of, are we going to be tested on this? Okay, if it's on here. All right, so first thing, you guys can read this. There's 3 sections on your test. And I mentioned this a little bit before as well. The first section is a very surface level knowledge in the form of fill in the blank, very short answer type stuff. Okay, definition level knowledge. Second section is going to be an analysis section. I might give you a line of code or 2 lines of code and say, what's going to happen as a result of this? Okay, or I might add a series of objects to a data structure and ask you what the order of the objects would be after they get added, testing your knowledge of stacks and queues and the order that stuff gets added, that sort of thing. Okay? The third section is free response, which I mentioned that before when we talked about stacks. Free response is going to be on your midterm, you're going to be filling in code. Okay, not a ton of code writing, but you are going to have to look at existing code and complete it. Okay? Questions on that? All right, let's get into the actual content of your midterm. Now, everything that we've got here comes directly from what we've talked about in class. Okay, nothing on your midterm is going to come from anything that we didn't cover in class. So you can always go back, watch the videos, review the topic outlines, look at the sample code that's posted. You're going to get your information there. Okay, so if you have questions while you're going through this list, while you're going through the study guide, go back and reference them in the previous stuff. They all come from class. Okay, so let's go through these rather quickly. Number 1, complexity analysis. What is the dominant term and how do we pick them out of a function? Okay? The dominant term assumes that you're looking at an algorithm expressed in functional notation. Okay, so think back to the dishwashing thing that we talked about. We have f of n equals 60n or something like that. The dominant term is the term that contributes most to the growth of the function. Okay, so it's the largest term. N squared is larger than n, and that sort of thing. Okay. Questions on that? All right, 2. Or B, expressing the algorithm complexity in big O notation. So once you've got the dominant term picked out, so if we have a situation where we've got functional representation like this, 15n squared plus 60n, picking out the dominant term, we ignore constants, we're left with 2 terms, n squared and n. N squared would be larger, so n squared is our dominant term. To express that in big O notation, we simply take that dominant term and put it inside of big O like that. Easy enough? All right, part C. Be able to analyze a non-recursive algorithm. And this goes back to that process that we looked at of how we go from a non-recursive algorithm, which is a looping algorithm, and we end up with its complexity expressed in big O notation. Okay. Some things that will help you along that process. Remember, there was about 5 steps to it. You need to be able to identify what that algorithm's basic operation is. Okay. The basic operation is the line of code that contributes most to its total runtime. Similar to a dominant term, but instead of where we're looking at a dominant term as functional notation, we're looking at the basic operation when we're actually looking at code or pseudocode. Right? Once we identify what the basic operation is, we need to express the number of times that basic operation runs compared to the input. And the way we do that is by setting up a summation. Okay? Solving the summation gets us the algorithm expressed in functional notation. And then we pick out the dominant term and put it in big O notation. We did lots of examples of these in class. So you go back and look at the topic outlines, go back and look at the videos for the non-recursive algorithm analysis. Okay, yes, sir.
Is that the one that was like cut off by 20 minutes or something?
Yes. So good luck.
Okay.
There was, if you look, there was 2 class periods that we did that. I believe the first day got cut off. So if you look at the second day, I think we just did examples that second day. So there's 2 videos. Long story short, there should be enough content that you can go back and review. I'll need to fix that next semester. I don't know what happened to it. Blame YouTube. All right, questions on 1. Complexity analysis. All right, 2, queues. Stacks and queues, I'm going to ask you the same set of questions. Okay, so you need to know these. Let's do these both at the same time. So queues, where are new elements added to a queue? The back. Okay? New objects get added to the back of a queue. Where do new objects get added on a stack? The front or the top. Either is fine. Okay? Objects get removed from where on a queue? The front. What about a stack? The front or the top. Okay, same thing. Given an implementation, determine the order in which elements are removed. So, if I said, let's say we have a queue, and I add the numbers 1 through 10 to the queue in order. So 1 goes in first, then 2, then 3. And then I said, after I've added 10 numbers, if I call DQ, which number am I going to get? You should be able to tell me that we get 1. Okay? Queues work first in, first out. Okay? Questions on that? Yes?
You're recording this, right?
Yes.
Okay.
I know I'm going really fast. Yeah, you go back and watch this. I'll put this up today. In a stack, if I added the numbers 1 through 10 in order, and then I popped, what number would I get? 10. Last in, first out. Good with that? All right. What is the cost of the NQ and DQ operations? Now, when I say cost, that refers to its complexity. So NQ, DQ is O1. We have direct access to the front, direct access to the back. NQ and DQ run in constant time, which means it does not matter how many objects are in the queue, we're going to get the same number of operations for adding and removing. Okay. Pop and push, O1. Same thing. Doesn't matter how many objects are in the stack, cost is O1. It's running constant time. Now, typically speaking, as we go through the rest of the data structures, we're also going to look at the complexity of the search operation. We don't talk specifically about searching a stack and a queue, and the reason for that is you shouldn't do it. If you need to search a stack or a queue, you're using the wrong data structure. Okay? For your own information, the cost to search a stack or a queue is ON, which is not good. Again, if you need search functionality, don't use a stack or a queue. All right? Questions on stacks or queues? Oh, what types of pointers use? Okay, then. So, in a queue, we use a head pointer and a tail pointer. We call it first and last. And in a stack, we only use a head pointer. We don't need access to the back of a stack. We only need access to the front because we do everything from the front. All right, one more thing and then we're done. Linked list. So far, we've used linked list as a base data structure. Okay, we didn't really do anything with linked list on their own. We used linked lists to implement our stack and implement our queue. Okay, we can use linked lists on their own, and there are different types of linked lists, but we didn't really get into that. Okay, we just used a singly linked list. But we use them rather heavily because that's how we implemented our stack and queue. So the first thing you need to know is how the list is constructed, how linked lists are held together. If you think about an array, we all know how these work. Arrays are simply a series of consecutive memory locations that are divided up into chunks or elements that we access those using index numbers. With a stack or a queue, each element or each object simply holds a reference to the next one on the list. There are no index numbers. This is not an index list. The only way we can get access to the third object is by going through the first to the second to the third. Okay? Typically speaking, the linked list will hold a reference to the first object in the list. This is so that we can get access to the list itself, because once we have access to the first, by definition, we have access to everything else. Okay. Understand how to add elements to the front of the list and shift the current elements using code. This is an example of the push operation of a stack. And I'll go ahead and tell you, your free response questions will be on LinkedIn. Just so you know what to say. I strongly suggest you look at the code for stacks and queues, specifically enqueue, dequeue, push, and pop. Those are what you should be familiar coding. Okay? Giving you a hint as to the content of your free response section. All right? And the last thing is understand how to determine if the list is empty. Go and look at the isEmpty method. So if the first reference is null, then you know nothing is in the list. And that's your midterm. I know I went through that really quick, but it's on tape. You can rewind and play and do it over again. But what questions do you have for me? Can I answer any questions that you guys have? Yes?
Would there be a curve?
I have never needed to curve.
Was that enough?
It's not a no, because if there's a need to curve, I will curve it. But, and there are different teaching philosophies. Some instructors like to make their tests extremely hard and then curve from there. I don't do that. I make my tests based off of what I think you should know. And then I try to prepare you to be able to demonstrate your knowledge of that. Not saying that one is necessarily better than the other. I prefer the way I do it. And all I will say is I've never needed to curve before. And I've been doing this a lot. Okay. I'm sure you'll be fine.
I'll put you down some maybe.
Okay. I'm not saying I'm opposed to curving, but to me, if I need to curve my test, I did something wrong. That's how I feel. But again, there are different philosophies. Other questions?
To meet you before going there.
Okay.